So hi everyone, myself Dr. Shushmita Sharma and I did PhD in Chemical Engineering and have around 5 years of teaching experience. So today I'm going to discuss one of the topic from Chemical Reaction Engineering, that is the design of reactors. So let's start. Now the introduction. So what is the reactor? So general definition of the reactor is a vessel designed to contain chemical reactions is called a reactor. Means, for example, if you want to proceed any chemical reaction, for that you need an equipment, and that equipment is known as the reactor. Now in reactor design we want to know what size and type of reactor are the best for a given job. Here size means the volume of the reactor, means for a given conditions, or we can say for a given conversion, the reactor which requires smaller volume is the best. And now the types of reactors. So based on the modes of operation, there are two types of reactor: batch reactor and continuous reactor. So in batch reactor, so this figure 1 shows the batch reactor in which we have a tank, so in which a stirrer is provided. So suppose we have a reaction like A, that is the reactant is going to convert in product P. So what we do here, we just fill the reactant A inside this tank, and once the entire amount of reactant A is filled in this tank, we leave it, we close the tank and leave it for certain period, and after time T we take the product from this reactor. So here in batch reactor we can say that during the reaction we cannot add anything inside the reactor and we cannot remove anything from the reactor. So this is about the batch reactor. Now another type of reactor is the continuous type of reactor. So there are two types of continuous reactor: CSTR, that is the Continuous Stirred Tank Reactor, and the PFR, plug flow reactor. Now what is the CSTR? So this figure 2 shows the CSTR in which we have a tank in which an agitator is provided. So here we are providing continuously, means the feed stream inside the tank, and simultaneously we are removing the product from the tank. So the molecules coming with this reactant, when they come in the contact with this agitator, the mixing of the molecules take place in the random direction. So it has uniform mixing throughout the reactor. So whatever the concentration of the product we are getting at the outlet of this reactor will have the same concentration at any point inside the reactor. So this is about the CSTR. Another one is the PFR. So in PFR we have a tubular type reactor. So the feed is entering continuously from this side, and simultaneously we are receiving the output from the another side. So here in PFR the mixing does not take place in axial direction. Mixing take place only in radial direction. So this is about important thing about this PFR. Now the batch reactors are generally used for the small scale plant, while the continuous type of reactor are generally used for the large scale plant. Batch reactors are generally used in pharmaceutical industry, and the continuous reactors are generally used in the continuous production of chemical products. Now so batch reactor, so we are going to derive the design equation for batch reactor. So general mass balance equation for batch reactor is input is equals to output plus disappearance plus accumulation. Now this is the general mass balance. So here in case of batch reactor, as we already said that in batch reactor during the reaction we cannot add anything inside the reactor, that's why input is 0, and similarly we cannot remove anything from the reactor. So here output will also be 0. So now we have only these two terms, disappearance and accumulation. So suppose we have a reaction that is A, reactant A is going to convert into product P. So here this disappearance term can be written as rate of loss of reactant A within the reactor due to chemical reaction will be equal to minus of rate of accumulation of reactant A within the reactor. Now disappearance of A by reaction in terms of molar flow rate, that has the unit moles per time. Actually we are writing all this term in terms of molar flow rate, so it has the moles per time unit, is equals to minus RA into capital V, where minus RA is the rate of disappearance which has the unit of moles of A reacting per time per volume of fluid. Now here capital V is the volume of fluid. Now the accumulation of A, again in terms of molar flow rate, it can be written as moles per time, which equal to dNA over dt. Now here Na is the moles of A, which can be which can be written as Na0 1 minus XA. On differentiating this Na0 is the constant term, so it is 0. Now we have minus Na0 dxa over dt. On substituting these in equation 1, we have, so this disappearance and accumulation term we are substituting in equation 1, and we are getting minus Ra into capital V is equals to n naught dxa over dt, equation number 2. Now on rearrangement and after integration, we get of this equation number 2, so we get t is equals to n naught integration from 0 to xa dxa over minus Ra in over V. So here this n naught over V we can write C naught, because n naught over V is C naught, initial concentration of reactant. So T is equals to C naught integration from 0 to xa dxa over minus Ra. So now this is the design equation for batch reactor. So the graphical representation of this design equation is shown in this figure 4. So this xa is over on x-axis and 1 upon minus Ra is on y-axis. So if we plot it, we have curve like this, and the area under the curve will give the value of T by C naught. So here T is the residence time, which is defined as the time spent by the molecule inside the reactor. So this is about the batch reactor. Now the CSTR, that is the Continuous Stirred Tank Reactor. So figure 5 shows the CSTR reactor, in which these are the input stream. So suppose we have a reaction A is reactant, which is going to convert into product P. So initial concentration of reactant A is C naught, and initial conversion is initially we have 0 conversion, so it is 0, and V naught is the volumetric flow rate and F naught is the molar flow rate. Now we have made certain assumptions on this reactor, like it run at steady state with continuous flow of reactant and product. The feed assumes a uniform composition throughout the reactor. Now the general mass balance equation can be written: input is equals to output plus disappearance by reaction plus accumulation. So now we are actually, the accumulation is 0 because it run at steady state, and under steady state condition this accumulation term will be 0. So now all these terms now we will write in terms of molar flow rate. So input of A in terms of molar flow rate, again it has the unit of moles per time, is equals to Fa naught 1 minus Xa naught. Initially we have 0 conversion, so this Xa naught is going to be 0, so we have Fa naught. This term is Fa naught. Now the output of A in terms of molar flow rate can be written as Fa is equals to Fa naught 1 minus Xa. Now the disappearance term, that is the disappearance of A by reaction, again in terms of molar flow rate, can be written as minus Ra into capital V. So minus R is the rate of disappearance, which has the unit of moles of A reacting per time per volume of fluid, into capital V is the volume of reactor. Now the component valence for A in terms of molar flow rate, so we are substituting all this in equation 4, and we are getting Fa naught is equals to Fa naught 1 minus Xa plus minus Ra into V. So here after simplifying this, means Fa naught and Fa naught will be cancelled out, so we have minus Fa naught Xa plus minus Ra into V. That after simplifying this equation, we get Fa naught Xa is equals to minus Ra into V. Now on rearrangement of equation 6, we get V by Fa naught is equals to Xa over minus Ra. So this is the equation number 7. So we know that actually this Fa naught molar flow rate can also be written as C naught into V. C naught is the initial concentration and small v is the volumetric flow rate. So we can replace this Fa naught by C naught into V in equation number 7, and we get the equation number 9. So here this capital V by V, again this capital V is the volume of reactor and small v is the volumetric flow rate, and the ratio of these two is known as tau. Now the volume of reactor over volumetric flow rate is tau. Tau means here the space time. Now what is the space time? Space time is the time required to proceed one reactor volume of fluid under a specified condition. So this is the tau. So we can replace this V by the tau. Now we have the equation number 9 in terms of tau by C naught is equals to Xa over minus Ra, equation number 10. So now this so what we can do here, we can compare this equation number 10 with the 7, and we can write V by Fa naught is equals to tau by C naught is equals to Xa over minus Ra, equation number 11. So this is the design equation for CSTR. Now the graphical representation of the design equation for CSTR is shown in this figure 6. So here we can see that Xa is on x-axis and 1 upon minus R is on y-axis. So now we have the curve like this, and area of this rectangle will give these two terms, V by Fa naught or tau by C naught. So these two terms can be calculated by this area of the rectangle. Now So next is the PFR. This is another type of continuous reactor. So figure 7 shows the this PFR, which is tubular type of reactor. So here these are the input stream, and so again we have a reaction. A is going to convert product P, so reactant A, and now we have made certain assumption on this PFR, like it run at steady state with continuous flow of reactant and product. There is no axial mixing of fluid inside the reactor, which we have already discussed. There is complete radial mixing of fluid inside the reactor. So we have actually made the material valence for the reactant, that is the component A, on this differential element of volume dV. So we have made over this section the material valence. So input is this Fa, is the molar flow rate of A, and this is the output. So now the general mass balance equation can be written as input is equals to output plus disappearance by reaction plus accumulation. Now again the accumulation term will be 0 because it runs at a steady state. Now the input of A in terms of molar flow rate can be written as Fa, and output of A in terms of molar flow rate it can be written as Fa plus DFA. Now the disappearance term, disappearance of A by reaction, again it has the unit of moles per time because it is in form of molar flow rate, can be written as minus Ra into dV. So minus Ra is the rate of disappearance, which has the unit of moles of A reacting per time per volume of fluid into volume of element. dV is the volume of element. Now introducing all these term in equation 12 we get. So after substituting this all in equation 12 we get Fa is equals to Fa plus DFA plus minus Ra into dV. So Fa and Fa will be cancel out. We have now DFA and minus Ra into dV. Now this DFA can be written as, in place of Fa we can write Fa naught 1 minus Xa, and on differentiating this DFA, so Fa naught will be 0 on differentiating it. So we have only minus Fa naught into dXA. So in place of DFA we can write minus Fa naught dXA, and this will be minus Ra into dV. So on now on integration and after simplifying we get the equation integration from 0 to V dV over Fa naught is equals to integration from 0 to F dXA over minus Ra, equation number 16. So again after integration we get V by Fa naught is equals to integration from 0 to Xa dXA over minus Ra, equation number 17. So now which can be written in terms of tau, V by Fa naught is equals to tau by Ca naught is equal to integration from 0 to Xa dXA over minus Ra, equation number 18. Now the graphical representation of this design equation is shown in figure 7. So here we can see that Xa is on x-axis and 1 upon minus Ra is on y-axis. So the area under this curve will give the value of V by Fa naught or the tau by Ca naught, while in case of CSTR, area of rectangle will give the V by Fa naught or the tau by Ca naught. So this is the difference between the this PFR and CSTR. While we have seen that in case of batch reactor, similar type of graph we have plotted. So again it is same, because only the difference is here the tau, which is the space time, and in case of batch reactor we are taking the T, that is the residence time, so which is equal for constant density volume system. So tau is equal to T, that is the residence time is equal to space time. So thank you so much.